So now let's try to study the application for the instrument like this, one open end and one closed end. And we say that one of the famous example is the pipe organ. So pipe organ is a very widespread and used instrument in the early church and in the East Europe, in the Europe. So the fundamental principle is using the concept we just introduced you, but for sure, based on the structure, you can see it is more complicated. But you can see when the ladies we blow the air through the top of the bottom, actually that is also a very preliminary concept of the pipe organ. So this is one of the very famous places, which is in Philadelphia. You can see the size of the organ is so big. So let me ask a question now. Why we need to build an organ pipe with so big size? So which you mean? Does it matter I make it smaller or bigger? Why I need to use so many big space to build a pipe organ? So when you are still thinking now, let's try to take a look about the physics we just learned. So apparently, the frequency, or I should say, the wavelength, is related to the length of the pipe. Agree? So first, I want to remind you one thing is that no matter how long the pipe it is, as long as it is one open end and one closed end, the fundamental frequency is always equivalent to 1/4 of the wavelength. So this pattern is always true no matter how big the L it is. However, think about it. If you have a bigger and bigger organ pipe, which means your L is very, very tall, very big. So therefore, you still have these patterns. Your L is still equivalent to 1/4 of the wavelength, but which means that your wavelength now is very, very long. But what do I mean when the wavelength is very long? It means the frequency is very, very small. So it is considered a low bass. So which you mean by increasing the length of the pipe organ, you can actually produce the sound with a very low frequency. And that is the reason why we want to invent the instrument like this with occupy a very big space. And apparently, we studied so many things so far. So the sound actually can be related to a very important instrument in our daily life, the music. So we use different kind of instrument to play the music. So the music intrinsically is transmitted in terms of a sound to our ear. So what is the musical sound? So you can see that if you compare the figure A and B here, A is a sound wave, but it is considered as a noise. The second one is a sound wave, but we consider it is a musical wave. What is the difference? You can see that the noise here, they don't have the repeated pattern. So which you mean? They don't, when they pass through to your ear, they cannot form a harmonic in your ear. However, for the music, they have a frequency and wavelength and the speed well defined. So it is a repeatable one. So you can hear the harmonics now. This is what we mean by the musical sound. They are all sound wave, but one with a typical wavelength and frequency and the speed. And for the musical sound produced by the instrument, intrinsically, it is related to the standing wave. So for the guitar, which has the both ends fixed, they can produce the first harmonic. So it is both ends fixed, so it is note on both ends. The second harmonic, so which means depending on how you vibrate the string, you can produce different harmonics of the musical wave. And why it is important? Because you can see that even the musical sound wave you produce here, it is not a perfect wave, yeah? it is intrinsically a combination of the different harmonic. So for example, it is a combination of the first harmonic, second, and fourth. So this is a very crucial concept. The musical wave you hear, is actually a combination of the different harmonic mode. And what is a harmonic mode? It is the mode in the standing wave, produced in the standing wave. Therefore, you can see here, let's try to use this one as examples. So now you use the piano to play the note C. So what happens? So before I show you that, I want to explain you one thing is that when you definitely hear a lot of people when they say the tones. So what is the tones? Actually, the tones are composed of the superposition of many frequencies. And this is the so-called the partial tones. So you can see that the piano here, they have the frequency and wavelengths produced here, which is very similar to the clarinet produced. But you can see the combination is different. So therefore, let's use the piano as an example. If you strike the middle C, what you produce is a fundamental tone. The fundamental tone is produced by the first harmonic here. So it is composed of the fundamental tones with a pitch about 262 Hz. And also a mixture of the partial tones of the 2, 3, 4, 5, and so on. And the number and the relative loudness of the partial tones actually plays a very important role. They can determine the quality of the sound associated with the piano. Okay? So it is very important that the quality or the loudness of the wave is controlled by the higher mode of that. But intrinsically, they are all a combination of the different mode of the standing wave. So therefore, the sound from the practically every musical instrument is consist of the fundamental and the partial tones, and pure tones can only be created electronically. Okay, so pure tones means only one frequency, and this is only true, only possible for the electronic device. And I have shown you that in the chapter 9. How did you play the electric guitar? It's due to the vibration of string with a magnet, and they produce a difference of magnetic flux. So therefore, this is why this is the reason why they produce the tones difference. Now let's study another very important concept of this chapter, the Doppler effect. What is the Doppler effect? It is simply due to that the frequency measured is no longer the same as original frequencies was produced. And the reason why this will happen is due to that either the source which produced the wave, the sound wave, or the people observe is moving. So which means there is a relative movement between the observer and the source. So the frequency will be no longer the same. So let's use this bug swimming in the water as examples. So the top one is a stationary bug. He is just jiggling in the up and down. So you can consider it is produce a source of wave propagating outward. And you have two observers, A and B. So if the bug is just oscillating up and down, the wave propagated will spherical outward. So the frequency measured by the A and B will be the same. But now consider that now the bug is swimming toward to point B. Simultaneously, he still oscillates up and down. So they will continuously produce the wave propagating outward. But however, because the bug is swimming toward to point B, you can see that the wavelength between the bug and the point B, the wavelength becomes shorter and shorter, and the wavelength between the bug and A become bigger and bigger. So because the wavelength is no longer the same, which means the frequency received by point A and B is no longer the same. And this is the concept of the Doppler effect. simply due to the relative motion of the source and observer. The wavelength measure has been changed. So the example in our daily life is that everyone, when you take in your driver license test, you know that when there is an ambulance approaching or the fire truck approaching, you should park your car next to the road and you should let them pass through first. But how did you know there is an ambulance approaching to you? If you use your common sense to think, you hear that. And when you hear that, it is the frequency you hear become louder and louder, which means the frequency become bigger and bigger. Agree? So what happens is that when the fire truck or the ambulance is approaching to you, you are standing here. So the wavelength in between you and the fire truck or the ambulance becomes smaller and smaller. The wavelength becomes smaller and smaller. So the frequency becomes higher and higher. So that's the reason your ear can hear the difference, and you will say, okay, now it is closer. So let's park our car to the side of the road. But after the ambulance passing through and living away from you, you will hear that now the voice become less louder and louder, or you can say the frequency you receive becomes smaller and smaller. And that is because you can see the wavelengths produced from the ambulance or the fire truck to you become longer and longer. It is stretched, so which means the frequency is smaller and smaller. So that's the reason that if the source is moving, the frequency received will increase, but it will decrease when the source is moving away from you. And this is the Doppler effect in your daily life. So now let's look at our last conceptual quiz today. So if it is approaching to you, it means the speed is still the same, but the frequency will increase.